Welcome to Ask and Learn.
Okay, so in this problem, we're told that a star has a radius of 8.5 times 10 to the 8. And we want, what else are we told? And the peak wavelength is 685. So lambda is 685 nanometers. And we want to get the energy of a photon with that wavelength. All right, we can just use E as HF, and then F is C over lambda, so E is hc over lambda. H is Planck's constant, C is the speed of light, and lambda is this lambda right here. So I'm going to go ahead and plug that into a calculator. 6.626 times 10 to the minus 34 times 2.998 times 10 to the 8th, all divided by 685 times 10 to the minus 9. And so with that, I got, oh, is this right? H times C, 2.998, 3 times 78, 685. I get 2.8996, many other digits, times 10 to the minus 19 joules. So I will go ahead and write that out. So 2.90, let's see, 3 sig figs, 2.90 times 10 to the minus 19 joules. Just double check that digit. And we want to get the surface temperature of the star, so we can figure that out using Wien's displacement law. So for that, what we want to do is say that lambda times T is equal to 0.2898 times 10 to the minus 2 Kelvin meters. And we want to take both sides and divide it by lambda to get the temperature. So I'll just go ahead and erase that. So then we can get that the temperature is equal to this. And I'm going to go ahead and plug that into a calculator. 0.2898 times 10 to the minus 2 divided by wavelength. And then I get 4,230 Kelvin. And sorry, let me pause real quick. Okay, and then now we want to get the rate that energy is emitted from the star. And so, i.e., we want to get the power. And so we want to borrow some of the formulas from chapter 11. So that tells us that power is equal to sigma E, the surface area of the star, times T to the 4th. And so this sigma, let's see, is equal to, oh, I have to pull up the chapter again. 5.6696 times 10 to the minus 8. Emissivity is 1, and A is the surface area, so that's going to be pi r squared. So sigma E pi r squared. If you're not sure where this comes from, just review the chapter, chapter 11, or you can just Google Stefan's law. So if I go ahead and plug all of this into a calculator, let's see what I get, and I'll pause while I do that calculation. Okay, so with that, I get 1.65 times 10 to the 26 watts. And great, so let's see what else they want in this question. And then D, we want to get the rate that photons leave the surface of the star. So this is the energy of a photon, of a particular photon, and then this is the total amount of energy per unit time. And so let's answer the question maybe like in 1 second, how many photons have left. So after 1 second, we know that this much energy, this number, let me write down what I'm thinking. Ooh, I really don't want to use another page, so I don't want to lose all these numbers. So I'm going to kind of box everything up and then make use of my spare space. So after 1 second, we know that 1.65 times 10 to the 26 joules have been used. And then each photon has this many joules. So you can kind of say times one, you do sort of a unit conversion. One photon has 2.90 times 10 to the minus 19 joules. And then that's how you can get how many photons are emitted per second. So let's go ahead and divide out these numbers. So I'll take the last number and divide it by 2.90 times 10 to the minus 19. And so with that, I get 5.68 times 10 to the 44. Sorry, that should be a 4 photons. So that would be the number of photons. And I'll go ahead and label this little section D.